Can everyone see the notebook I have open?
Yes.
Okay, so I ran a few of the pieces early on. It gives me an error, which I'll fix later. It's not material to what I need to get done, what we need to look at here. I think Jeremy started moving things around again in the first day stuff. But what Jeremy does in this walkthrough is kind of take us through defining how transforms work and why he has implemented transforms the way he has and what are the changes. We'll see more of the usage in this notebook. And in walkthrough 5, and I'll post slides relating that at the end of this, after we get done with this lecture, but in walkthrough 5, he takes us through the tutorial on data block, and then subsequently gets into the transform notebook itself, which is in one of the core or foundational pieces of Python changes that he makes. But in this particular notebook, we're talking about more of the usage and basics of transforms and how they work and how he has designed them to work. And then towards the end, why pipelines are necessary and how pipelines are constructed from the basic transform. So we'll use kind of the different very simple examples to make the point. He, if you watch the walkthrough, he uses or goes back and forth and changes the same set of cells, but with a few modifications, but that gets very confusing, and he kind of live codes through the video, and that would be too confusing to keep track of, or I couldn't do that. So I kind of unrolled the loop, so to speak, and we'll look at it step by step. So essentially, we'll start with just using the MNIST tiny data set, and all we have done is sourced it, and from the source, we are just getting items through using the get image files function. And after getting all the image files, we just get the item 0, which is just a path to a particular file, which is a PNG file of the number 3 from the MNIST database. Now, let's suppose we define just a simple function, which is a negative of x. So let's say we define a function neg of x, and all it does is return minus x. So if we run that, we get minus 3, as we would expect. Now, the funny part is, if we were to try and execute this function on a tuple instead of a single integer, by first defining the tuple, and then if you were to negate the tuple, you'll see that Python doesn't let the function work on a tuple. So the key point Jeremy makes in this lecture, and as we get into the lecture 5, 6, and 7, you'll see a lot more of the details behind this. But the point he wants to make is that this is just a design choice in Python. The fact that Python converts or acts on x when x is an integer and you have a function neg, whereas it doesn't act on a tuple, is a design choice in Python. And that design choice can be changed, as we'll see, by the use of the definition of transform in the way Jeremy has coded or modified Python for the data science purposes that he uses this for in FastAI library. So the other interesting thing, for example, is while negation of a tuple doesn't work in basic Python, if we define an array, so an array is just one tree, it's not even a NumPy array, it's just a basic array in Python, and we do a neg of an array, it works. So it negates the elements of the array, as you can see. So the point is that these are design choices in Python, and Python provides us the flexibility to modify that choice. And how we do it is what we'll get into in subsequent lectures. But here, what happens and how we want to make it work is what he discusses. So Python lets us change the behavior. And obviously in data science, we want it to work on tuples or all the elements of a tuple, because typically in data science, we would have a tuple coming out at the end of the data pipeline before we send it for optimization and so on. And the tuple would typically, and there could be a variety of things. If we are working with images, the tuple could be X is an image and Y is a label for classification of images, for example. In segmentation, X would be an image, Y would be a mask. In case of a Siamese network, you would get two images. So X would have multiple values, and Boolean Y, which would be true or false, would say whether these two images are identical or not. In case of tabular data, you would get continuous variables, categorical variables, and both of them are different types of variables, but both are input, and then you would get the target Y, and depending on whether it's classification or regression, that would vary. But in all instances, you can see that there is an XY tuple pair that we desire. So what we would like in general is for Python to be able, or I should say our FastAI library to be able to support negation on a tuple, which native Python doesn't. Now, he already has designed or defined the transform function. So here he just uses the transform function he has defined, and it uses meta classes and stuff that we'll get into in the lecture after next. But right now, he just uses it as a decorator on the basic function negate that he has defined, or neg. So if you use the transform, which Jeremy has defined for FastAI, as a decorator on negation, then let's see what it does. So it will modify the negation function, which is just a simple Python function, to make it a transform. And when that happens, then the negation of the tuple works. So you can see that while we go ahead.
So Srinivas, if the tuple consisted of a number and a label, like a number and like maybe it was 3, the string red, then when you apply this, it'll still work, right? It'll just negate the 3, but it won't touch the red string.
Yes, that's what, and how that happens is what we'll look at in the rest of the lecture, and why that happens. So that's essentially what we're getting into next. So for example, let's say we load an image from the file name that we have already loaded up above and print it out. It's an image of the number 3. That's the tiny MNIST data set that we loaded. Then we are going to create a tensor from the image. So let's say tensor, and then we are making it an array, converting it to a tensor, and we make it a float, because otherwise it's a unsigned int, and because it's unsigned, it won't, running neg on it won't work because the underlying data structure doesn't support it. Anyway, to illustrate what we want to show, tensor image, and then just to keep things simple, he just indexes into it. So T image is a 28 by 28 tensor, of which, let's say we just select 3 rows of it. That's what you see here. But let's say we create the T sub, which is a subset of the tensor image. So here we have a tensor of the image, and then we index into a subset of it. Now, since T sub is just an float array, if you do a neg on T sub, obviously the relevant portions of it, or every integer or every float value, gets negated, as you can see here. Right? Now, let's create a tuple of T sub, which is 2, you just duplicate it and you negate it, and obviously.
Hello?
Yes.
I wanted to say that you tested what 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 was said, and if you negate two numbers and a string, you got an error
No,
for.
we'll see what happens. It depends
Yes,
on,
I just wanted to say that you need to your transform to be typed so that it only touch the int
yeah,
and
and
all that.
that's what we'll see in the rest of the notebook, how we make it work on portions of it and not on other parts of it. So that's coming up as we go through the rest of the notebook. In this case, he's taking us through that, how that works step by step. So you'll see that what we need to do as we go through the rest of this notebook. So let's say this is obviously a fairly simple function negation. It's not that complicated. It just negates the input that you provide. But let's say we want to do something a little bit more complicated, which is to say, let's say we want to normalize the value that we supply as an input to a function. So let's define a function, norm of x, and let's just also provide a means the ability to supply that function with a mean and a standard deviation. And we just define the function to be subtract the mean and divide by the standard deviation. And we supply the two values, m and s. So let's define that function. Now, he just chooses two arbitrary numbers for m and s. There's no particular reason those two numbers are chosen, but I stuck with whatever he chose. And so let's say we, on the image that we already imported, let's say we norm the tensor image with two values that I said before. Let's say we just choose two arbitrary values, 127 and 50, and supply it along with the tensor image, and we apply the norm function. And then to keep things simple again, we just index into that and look at rows 12 through 15. And what you see is the negation of every value of the tensor between the rows 12 and 15. And what it has done is it's taken those values, subtracted 127 from each of them, and divided them by 50. Now, typically though, as he says, since this is a subtraction and a division, but we would like to do it for a whole bunch of values, as you just see here, and we'd be executing it on a 28 by 28 matrix. We would ideally like to do it on the GPU because it would execute much faster. And as a couple of people who chimed in already pointed out, by the time we are in the data processing pipeline, deep into it, and we typically have an image and a label associated with the image, not just an image. So for example, it could be the image and the integer 3 to indicate the label. But again, since we just want to keep moving, let's say we just give it and to simplify the math, let's say we just give a tuple, which is the first part of it is the tensor image, and the second is an integer. Right now, we just pass in an integer 1. It could potentially eventually be like 3, or you could get some other function to define a label, and that's the label that you would get in the place of 1. But just for illustrative purposes in this notebook, let's just say the label we provide is an integer and its value is 1. So we define that tuple. And this is what, so the image tuple is typically what we would be working with at this level of the data pipeline. And what you see here is the entire tensor image. So it's like a 28 by 28 matrix. Now, so far from what we have defined, if we just execute the image tuple or the function norm on the image tuple and pass in the 127 and the 50, again, keep in mind that we have just defined norm to be the subtraction from the input that is supplied and subtraction of the mean and divide by the standard deviation. So that's all we have defined it as. So if we do that, again, we run into the error because this is the norm is just a function so far that we have defined. If we convert that into a transform by decorating it with the transform decorator, then you get norm, you convert the norm to a function, and remember that one of the things that transform does, or the transform decorator does, is the fact that it makes norm dispatchable, if you will, on a tuple. Then this, you don't get the error anymore and a tuple is supported. But now you see that when you run norm, which is a transform now, on a T image, this is obviously running on the T image, right? And again, he just does that to calculate. Now let's suppose we create a tuple of the tensor image is the first input or the first value in the tuple, and 1 is the label, it's the integer 1. We create that image tuple and then we run the norm on it. Then it works, doesn't complain, because the decorator makes the norm function, transforms it into a transform, and the transform works on a tuple. However, you will see there's one problem, and the problem is that it also converted the label currently. So what it does, if we just do what we have done so far, which is we have converted the function norm into a transformation, then the transformation supports a tuple as an input, but it applies equally to all the elements in the tuple. So not only did it normalize the image, which is the tensor image portion, which is the first part, it also normalized the integer 1. And if you do the calculation, what it did was subtract 127 from 1 and divide it by 50 to get the value minus 2.52. But obviously, this is one way to apply the transform, but not the way we would desire, because we want a way to apply the transform only to those items that we wish to normalize within the tuple. So for example, we don't want to normalize the label, but we do want to normalize the image. So what what Jamie has implemented and what he says, the infrastructure behind the ability to do this by modifying Python and so on, is you can add a type notation to say, apply to these portions of the tuple, apply the transform to certain portions of the tuple, but not to other parts of the tuple that I provide to you as input. So that's good, but how do we do that is still interesting, because by the time we reach in the data pipeline, the input of, by the time we are ready to provide the normed image for processing, both the label as well as the image are tensors. We have kind of converted both of them into tensors. So even the integer, for example, would have been converted to a tensor or a category tensor or of type tensor. So if everything is of tensor type, then it would be hard to say implement the transform on this tensor but not on the other tensor, and since both are of type tensor. So in order to avoid that problem, what we typically do is we create a subclass of tensor. So for example, FastAI has a tensor base class, which is nothing but, to illustrate it, here is the code for it. It's tensor base. It just in turn inherits from tensor. There's some class methods before casting, blah, 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 but not relevant to what we need to do here. So what we end up doing in order, and this is again done so that we can differentiate the tensors that we are supplying to the tuple, we create a subclass, call it my tensor image, make it inherit from the tensor base. Remember, tensor base, in fact, is also essentially a tensor. And we don't define any code in it. It's just to create the subclass. And so let's say we create the my tensor image, and then we define the MTI, the value, to be of type my tensor image and pass in the tensors to it. So now what we have created is, again, essentially a tensor, but its class is now going to be of type my tensor image. And it still has the values, which are all the tensor values from the tensor image. The only thing that's different about it is it's of type my tensor image, which inherits from tensor. So this has solved the problem for us of being able to provide a type to the first value of the tuple that we pass in to the transform and say that it's going to be of type my tensor image. And the transformation infrastructure has the capability to apply itself or apply the function that you define to be a transform on only certain types. So this is how he illustrates how it is useful to have that capability built into the infrastructure, and also how it is used and why it is necessary to define subtypes of base types like tensor in order to be able to handle them selectively during the transformation part. So now we can start constraining our function, which is the transform function, to work only on the things we want. So how do we do that? Well, we say the input X that I'm supplying to you, the portion of it which is my tensor image, apply the norm function to it. So now we begin to see the behavior that Joseph and I forget the other person, but they were commenting on, which is selectively apply the norm function on particular types and ignore the function when the type doesn't match. So now we see we again defined the transform, basically decorate the norm function, convert it into a transform. And because it's been defined on the my tensor image as X to then execute it, we define the tuple again. And now when we run norm on the image tuple, we expect it to work on MTI, but not work on one. And when I say not work, what it means is if you supply a value to the tuple or value in the tuple whose type does not match what you define in X here, then essentially the function will be a no-op. It will ignore that, but it will not do anything. It will return the value that was supplied to it. It does nothing, or it executes a no-op. So define the tuple, run it. And what do we expect to see at the bottom? We'll expect to see, instead of minus 2.52, which is what we saw when we ran the tuple, in the previous definition of transformation, where we did not constrain the transform to only apply to my tensor image, we saw that this number 1 was minus 2.52. Now, when we have modified the transform to only apply to the my tensor image portion of the norm function, or sorry, to the my tensor image type of X, when X is a part of, or X is the input, and MTI is of type my tensor image, 1 is of type int. So 1, when the transform is executed on it, doesn't do anything, returns 1. When, on the other hand, MTI, it norms the tensor image because it's of type tensor image, which we say execute norm on it.
Quick question, Srinivas. Can you go up, please? So where we are saying that norm need to be applied only on a X, not on a M, because X is defined as a my tensor image. I get that, because now this is a custom defined tensor as per se. But where we are saying the norm will get applied only to X? Because I see in the brackets it's X.
Yeah, that's part. I mean, this is the mechanism by which Python, when we'll see that when we get into the actual code for the transformation, which comes up, I think, 2 lectures down the road. The code which constrains execution of this function is actually achieved by the decorator transform that you apply to the norm function. We are not yet gone into how that works and the details of how that is supported. The function dispatch code, the fact that it's a meta class, the fact that you can supply, as you can see here, an encoder function to it, a decoder function to it, things like that. We will be, an order based on which it will execute. We saw that a little bit, I think, when QB was lecturing on the second walkthrough, but we'll see the details of the transform code and how it is supported in the lecture after next. If you're lucky, we'll get through some of it toward the end of the next lecture, but then most of that will come up in the one after that.
So even if we look at the definition of a norm here as we are applying or calling a norm function, can I say here that if we have a custom defined tensor, then the transformation would be a different. If the X is a predefined tensor, then transformation will be applied to all the parameters of the norm function. However, when we have, is that correct assumption?
I don't quite understand or follow what you mean by predefined, but here's how I would phrase it. Because what we are doing is defining a type to X and constraining the application of this function when decorated by transform to only the type that we supply to X. And we'll see that in a minute. So in a minute that you can change this norm function to only apply, for example, to the integer 1 and not to the image MTI. Okay, and that will probably clear up your confusion as to how we can constrain it to apply to certain parts of what we remember. X is the input we are supplying, and it's a tuple, and every element of the tuple can have a different type. One can be an integer, another can be a float, a third can be my tensor image, a fourth can be a tensor. What this X colon this format in at least FastAI, I mean, it has other uses in generic Python, but in FastAI, the X colon my tensor image says if a class of, if the type of X that I supply to you is of type my tensor image, execute the norm function on it.
Okay.
And ignore if it's of anything else. So if you were to supply a tuple of not, MTI 1, 1.03, another just a tensor, it would only work for the closest type where it matches. So MTI matches my tensor image, so it will execute it for MTI, but it will ignore it for any other value that you supply to it in a tuple. And we'll see that because we'll flip it from supporting or executing on my tensor image type, and instead we'll say execute on the int type, and that is coming up a little bit later. So it's more that by providing this kind of capability or type labeling, we restrict it. Now you could have an immediate question, and we'll also see the answer to that in subsequently. What if I wanted to execute on multiple values of a tuple? So I wanted to execute on a tensor image. I also wanted to execute on the int. Yeah, I wanted to do what it does, that is the norm, on both those values. How do I accomplish that? And we'll see that in a minute as well.
Okay, just last question before you proceed. Here, the my tensor image is a type of a tensor base. Why did we have to create a my tensor image as a class? Why didn't we apply tensor base directly to the X?
Because I mean, tensor base is basically a base class of tensor. That's in FastAI. I mean, you could have created my tensor image of tensor class itself. But I think he has a base class defined, and so he in FastAI, and so he just uses the subclass of that. The important thing is that it needs to be subclassed from tensor. Why does it from a tensor base? That's a good question. I don't know specifically in this instance why instead of using a tensor subclass, he uses a tensor base subclass, or by that I mean he uses my tensor image and subclasses it from tensor base instead of from the tensor itself. There may be other reasons that I haven't quite.
Yeah. I think it's to keep things consistent because, you know, over time he does like tensor image, tensor bounding box. They're all subclassing, they're all superclassing the tensor base. So he just wants to like keep that flow consistent in the example.
Yeah, I mean that's what I thought too. That in FastAI, tensor base is the base tensor class, so he wants to be consistent to make all of the subclasses of the tensor base. And the reason he creates a tensor base is he probably doesn't want to screw with a basic tensor definition in PyTorch, but doesn't, wants to subclass it from there so that he can make some changes in tensor base, which the tensor in PyTorch doesn't support. So in fact, we saw that tensor base did have some additional code. It wasn't just a simple pass. So he's obviously doing things in tensor base. So the tensor base class of FastAI is not identical to the tensor in PyTorch. He's doing some other things which he may find useful elsewhere.
So maybe this is a dumb question, but why couldn't he just say, force the type of X to be tensor,
because,
or tensor base class, or why does he have to create a separate tensor image class?
That's in fact the foundation. So let's take with the first part of the question, because once you make it a tensor base, then you're obviously split it from a tensor. And as the person prior just explained that he just wanted to be consistent and make a base class from a tensor. But sticking with your first part of the question, which is relevant, of why does he subclass it from from tensor base? That is because of what I had explained originally, which is by the time, and in this case, we have not done that. He just wants to keep things simple. But typically when we get to this stage of the data pipeline, if you recall, both MTI, for example, would be a tensor, and one, he stuck in one and made it an integer, but typically this would also be a tensor.
Oh, okay.
Both of our values are tensor. How do we distinguish between the first one, which is an image, and the second one, which is some category or an integer or a label? In order to be able to distinguish, he introduces the types. And the types help us limit the application of the function to particular values, which are of that type, and ignore other values which are not of that type.
Okay, thanks.
Okay, so any other questions? Okay, so if we keep to the next, so as I said, now the one thing he illustrates, which again is, if you think about it, interesting, because when you use a language, you just kind of use it and think this is the way it works and this is the way it shall be. But his point is a valid one, and it got me into portions of Python that I wasn't familiar with, and it's of interest by itself. But the point is that this way of working, by this he means this way of working, meaning, depending on the type, I'll do something different on different values of the tuples that you supply to me. So if the first part is a tensor of type my tensor image, then I'll norm it. And if it's an int, I'll ignore it. His point is that this is no more strange way of doing things than the Python default way of doing things, in which if you supply me a tuple, I'll give you an error, and I'll only expect to work on int values or an array values, but if you give me a tuple, I'll give you an error. So in the native Python way is just one way of dispatching functions. And the way Jeremy has modified Python to work now with the transformation and the support infrastructure that we'll get into later is just another way of Python dispatch. So the point he wants us to understand is there is, this is not by any means strange. There are languages which handle elements of the tuple the way he has modified Python. I think he says Julia does that. Yeah, right there. On the other hand, Python doesn't, and he wants Python to behave the way Julia would, and so he just changes it. And how he does it, we'll see, as I mentioned, in a couple of lectures from now. So the question is, do transforms only apply to tensors? I mean, does it have to be a tensor in order for the transformation to work? And just as I mentioned before, he goes on to show that that is not the case. I mean, you can pretty much apply it to anything. So let's say we define a subclass, and again, we define the subclass in order to be able to say execute on this subclass or not on other subclasses and so on. So let's say we define a myInt subclass, which is subclass from int. It does nothing, but it just creates a type. And we now make mi of same value, integer value 1, but it's now going to be of type myInt. Right. So if we did type of my I, it'll tell us that it's of type myInt instead of int. Right. And now let's again define the norm. And this is an example of where he goes back and forth in the walkthrough, and I kind of unroll the loop because it gets very confusing. And let's again define the tuple. Now keep in mind that the tuple is mti, which is my transform, my tensor image, and then myInt. And remember, in this case, what we have done, I think it was Dinesh who asked me this earlier, but notice this, that we have defined X now to be, or we have more properly, I should say, saying if X is myInt, execute this function, and if it's not, ignore it. So what you ought to expect when you do this transformation and provide this tuple is the fact that this norm function will now execute on the first part, which is, will now execute on the second part, which is the myInt, because that's what you say execute on, and it'll ignore the image. So it'll norm the integer. So you'll see minus 2.52, and it'll leave the image part or the my tensor image part without any norming. And so it'll remain as its original value. That's what we should expect. And let's see what we get. We do the norm, supply same values. You can see that it hasn't touched the image. It's actually did apply the norm to the integer or myInt value in this case, right? So that's how we constrain it. One thing we haven't yet answered, and we will in a few minutes, is, hey, what if I want to execute on multiple portions of my tuple? And how do I do that? And that it will be illustrated shortly as well. So we are back to defining norm the original way. In this case, now again, I'll call your attention to the fact that now we are saying if it's a tensor, we are defining norm and decorating it as a transform. So if it is a tensor, do the norm is what we're saying here. So one issue, and this is more a simplification of the function, if you will, is that instead of passing m and s every time, you pass it once, create a partial, and then use it ever after. So actually, there's no reason to run that. But let's say f is a partial of the norm with the passed in values of a mean and a standard deviation. Then a norm image can become the partial function with the m and an s. And obviously, in Python, a partial means that you have predefined MNS to be fixed values, and f of tmage therefore executes the function, which is the norm function, but with predefined values of MNS, and execute it on the tensor image. Remember that we have changed this to be tensor, so it will execute on the tensor, and then we look at the part of it here. Right, now keep in mind, this is not a tuple, this is just the tensor image that we executed it on. So now image tuple, t image mi, so let's say we create a tuple and we do that, we execute it on the tuple, and it's a tensor. Now remember, this is an int, it's not a tensor, so it won't execute on one, but it will execute on the rest of the image, right? Then a few other things that we actually want to do with the norm transformation is we may want to serialize it, meaning we want to situate it within different parts of the pipeline. We want to be able to save the M and the S that we calculate to the disk. The other interesting and more useful thing we want to do with it is the fact that once we normalize, obviously we'll be supplying it to the optimization function further in the data pipeline and so on. But if we want to display the image, we want to take it back. That is, we want to denormalize it. And that doing these type of things requires that we able to store the value of the image or store the normalized value of the image. Once we need any kind of storage, then we cannot just use the decorator on a function to make it into a transform. There are multiple ways, and we'll get into all the different ways in a subsequent lecture as well. But so far we have seen the simple way of making a function into a transform, and that's just by decorating it with @transform. But that doesn't allow us to define state within the transform. That is to store variables within the function that we define. So if you want to define a function and also store some values, then obviously we need to define a class rather than a function. So we can define a class and make it a transform and how we do that is by defining the function, but inheriting it, or defining a class. We give it the same name as that of the function. So it's a class now, but then we inherit from transform. So this class norm is now a transform or a transformation actually. So this is the second way of making a function a transform, is by defining it as a class and inheriting it from transform. So here all we are doing is, and again, in this case, we don't save too much of typing, but he uses his store_attra self ms, which is equivalent to self.m, self.s is mns. And we also inherit, or we call the init function of the transform. That's what super init is, which means we have actually inherited from the superclass of norm, which is transform. And then here's the important part. If you recall from our previous lectures, transforms typically have, I mean, they may have multitude of things, but at least they have three things. One is encode. So when we call the transform, as I've said before, it runs the encode function, encodes function of the transform or the class. If we say, norm.decode, then it runs the decodes function, and then it also runs setup. But right now, let's just say we are defining encodes, and much like when we were doing @transform decoration and then giving it a type to limit the execution of the function or the transformation on that type, we do the same thing by saying if x is of type tensor, then do this. So again, in this case, the advantages are that M and S can be stored. As we will see in a minute, we can define encodes, decodes, and stuff like that, as well as do some setup. We limit the execution of this transform to a particular type when we pass in a tuple, and the type should be of type tensor, at least for this definition of norm. So let's go ahead and execute this, define this class, define the mean and the S. We need to create the M and the S, then create the partial of this class with M and S. So by executing F equals norm, M equals M, S equals S, what we are doing is initializing the MS values and storing them as attributes in this class. And F is an instance of the norm class, so we do that. And then we pass in the image. Now, this is not a tuple yet. Keep in mind, in this case, we are just passing in the tensor image and looking at whether it's converted it, which it has or will. And now we can again define the tuple. Let's keep the int portion as myInt type. So obviously, whether it's an int or whether it's a myInt, this definition will not execute on it because it only executes on a tensor if the type matches, and if the type is of the input is of type tensor. So we define the tuple and execute the transformation. And what we have to expect is while all this gets transformed, the one doesn't get transformed, right? Any questions to this point? Okay, if not, now let's see how do we do the transform on multiple pieces of types. This was something else I had alluded to that we'll see an example of as we move forward. So not only do we want to execute the norming on the image, for whatever reason, let's say we want to norm the label as well. For a minute, let's ignore that. That's not how we would like this part to work, but let's assume that for some reason we wanted this capability. Then one way to define it, and this would not work in standard Python, defining multiple encodes within a class. Don't recall now whether it actually complains or whether it just uses the last definition that's given of a method. You can go ahead and try it. I did try it way back. I forget now whether Python complained or whether it just silently used the last definition of the method. But be that as it may, in this case, what we are defining is exactly the same code as before. The modification that you will see is the fact that we have multiple encodes. So one encode says if the value of what I supply in the tuple is a tensor type, do this. Obviously, in this case, we are doing the same thing for both. But the point is, if the match or if the value in the tuple is of type int, do this. And obviously, for any type that's not specified, it will do nothing. So now let's execute this, define this class. Now, this is one way of supporting multiple types for the values of the tuples that you supply. The next three cells, by the way, are identical to this, but just a different way of doing the same thing. So I'm going to execute the cells, but they come, what you need to understand is this particular cell, let's see what the number is, so I can refer to it, 62 is one way of defining a transform, the norm transform, which works on multiple types. That is, it works on the tensor type, it works on the int type. The next three cells, this one, and these two together, all of them are a batch of cells that you would need to define, or you could define it all in one cell, I guess. The point being that this is a different way of supporting the same capability as what I've defined here. So let's just look at that, what it does. So it has the same code, and until it gets to this point where it says, oh, if my input is a tensor, let's say return blah, blah, blah. Then what you do is you define an empty class in which there is no code. So you empty the class definition once. So you say class norm transform pass, so there's nothing in it. And then you use the norm decorator, which is since transform is a decorator and Jemmy has built in this capability, now you can use norm itself as a decorator. And then you define the encodes portion of this norm transformation to work on a tensor. And then you define another encodes to work on an int. So in a way, this is even simpler way of just extending the definition that you have in a base transform by defining an empty definition and then having decorators of that transform and then defining all the types that you wish to support. So this is just two different ways of doing it. In this, all the code sticks in one place. In this case, it's more dynamic than that, but this is useful. This way of doing it, the second way of doing it it's also very flexible and useful because, as an example, he gives this case of, let's say we are norming an audio function. And let's say the definition for norming an audio file or a input tensor, which is an audio tensor instead of my tensor image, let's say it's of class my audio tensor. And suppose this function were to be different than what you define for an image tensor, you could just define at norm def encodes and then change the function here and change the type here, and it would execute differently on an audio tensor. So this really gives you the ability to augment your data or transform your data in whichever way you want and extend the type or the definition of norming or any other transform to support a variety of data types very flexibly, right? So that's
quick question, Srinivas. So in a first set, the encodes, like the encode, I'm talking about cell number is the down below the next cell. So the encodes is repeated twice for a tensor. Are we supposed to have twice, like once in another the one cell where you have another way and one?
Yeah, it's a good question, Dennis. I think what I believe is you do need a base encodes here to do something. And then by defining the empty class, and then because you have emptied the class, this is the thing that it will think of. I have not tried, and you can try it yourself. I don't want to try it here now because you can screw up the rest of my
it works
notebook.
without that.
But sorry, but let me just finish my thought and then.
Okay, sorry.
The thing you could try is removing this encodes and not having it in the base definition of your norm, emptying the class here, and then defining it only in these two places. So your question is, does this need to exist? Yeah. I haven't tried it without it. You may want to try. I don't know whether it will work or whether this line needs to be here.
Okay.
Or for that matter, the other thing I believe, and one other thing I wish to say is, I think because you empty the class here, I anticipate that you would still need this definition of the encode tensor to execute if you have done this. I don't know whether you need that if you have these three cells to follow, but you can play with it to see what works, what doesn't. Sorry, somebody was going to say something else.
Yeah, I think it works without the encodes, like in the norm.
Okay, so you're saying you can get rid of this highlighted line and it will still work. Yeah, that could very well do the work because, what you're doing is you're kind of redefining the norm transform to just be a decorator, if you will, with nothing here. So I would anticipate that should be okay.
Yeah.
So
but one thing I think which is true is I don't believe unless you initialize the M and the S that it wouldn't work without this part.
Yeah.
It may work without the encodes line, but you still need to do this part.
Yeah.
Yeah, because you're calling it down there.
Yeah. Another question I have is with regard to this empty class definition once. Is this like when we empty the class, is this we are making the way that we can use a decorator?
Yes, in a way, that's what we are doing. Is then you can do the at norm. So actually, I think even this thing does it, but I believe I haven't tried it again without defining the empty.
Yeah, I think that will work too.
If you have defined the class norm, then it is possible that since you're inheriting from transform, and transform is the base capability of a decorator, this particular thing, if you ignore and you just did these two and didn't have the encodes and you just had the init, that is possible that it will work as well.
Yeah, it's
I haven't played with all the variations. You can try. I think
Okay.
the two things that we agree on is likely to work is getting rid of the encodes and then just having this definition and then doing these two lines. Similarly, I believe if you drop this but have the base class, you can get rid of the encodes, just have at norm this and this. You can try that as well. And again, I didn't want to screw with it partly because he was modifying these definitions in the walkthrough as he was doing them. So what happened then as he executed may not be what you see now.
Okay. Thanks.
I think we are watching like some magic, because I am not so sure, but I think you can use like a class, a normal Python class, as a decorator of a function. So I think when you subclass from transform, it also gives you that ability that the classes you created from transform can make this like decoration.
Yes,
Because
that's kind of what we agreed. However,
okay,
the important point is because you're inheriting from transform, you can define multiple encodes. You can't do that with a normal Python class.
and also going back to what he wrote about that the not applying the transforms to a tuple is a design decision. I think with these encodes and decodes typed, you can think of like a rise of the same thing. I mean, if you apply a list, a map on a list with that has integers and strings, and you do an application of a function that subtract two, when you do that map, when it gets to the string, it will throw an exception error. But with these transforms, if you apply the apply encode, it will like you select the ones that match the type, and the ones that doesn't match the type, instead of throw an error, is like I just skip it and let it add alone. So I think we are watching a lot of nice things that are not so common to do, because you could apply a map over a list and it will apply. But with
Yes, and
transforms, you have
we'll
more.
see how that's supported when we come to the detailed code of transform as well, that it works on tuples, but in case of list, what does it do? And there's a subclass of transform called item transform, in which case it applies to things like list, but for tuples, it behaves, or it assumes that the default input it gets is a tuple. So yeah, it provides a lot of flexibility, and we'll see how that flexibility is provided as we get into the definition of the code within the transform class in, I think, 2 lectures from now. Okay, so moving on, I believe I executed, well, I didn't execute that. So once, excuse me. So this is the way that you can support, if you will, multiple. But here he wants to illustrate something in the next couple of cells, which are kind of fascinating, just to show you how the matching of this particular dispatch function and the capabilities that he has built into transform works for specific classes. And what I mean by specific classes will become clear in a minute. Keep in mind that, excuse me, so what we're defining now is a class norm, and this code is identical. The encodes, we provide 2 values, and we want it to execute. If it's a tensor, we want it to print A and then norm it. If it is a type my tensor image, then we wanted to print B and execute the norming. So you can see that depending on the type of tuple value that's provided, that is tensor or tensor image, it will give us a trace, meaning it will print A, or if it executes this code, and it will print B if it executes this part of the code. Now, that's what the definition of the norm in this particular instance. We are defining the norm transform to be this class. And then we define the M and the S. Let's say we do the partial. And now here is the interesting thing. We pass it the my tensor image type of input. It's not yet a tuple, but it's just a single value. And we are executing the transform F on the my tensor image. The question is, my tensor image is a subclass of tensor base, which is a subclass of tensor. So the question is, which of these two pieces of code will execute? And the point he wants to make, excuse me, is the fact that the code that executes is of the subclass that's it closest to the class wherever, it will execute the code which closest resembles or matches the X type that we provide. So in this case, since MTI is of type my tensor image, what it will do is it will execute the encodes function defined for this type. So if you execute that, then you can see that the first value that's printed is B. So even though MTI is of type tensor as well, because remember, my tensor image inherits from tensor base, which inherits from tensor, the code that executes from this transformation is the closest subclass match. Why this is relevant, it will become clear as we go forward, because when we decode, we wanted to use the closest match in order for it to be able to display what we want. So that's kind of what he explains here. Notice that this prints B because my tensor image is further down the hierarchy than tensor and is the more specific type match. So it encodes uses the most precise type match that it can. Okay. And now here is another version of the norm. And in this case, we are saying tensor and we are using a numbers.integral, which is actually a base class, abstract base class. So int, as it turns out, is a subclass of this abstract base class. So what will happen when we execute this transformation is the fact that it will ignore the it will ignore, if we pass in a tuple, it will ignore the MTI part, which is the, because there's not an exact match to a my tensor image, but int is of type subclass. Actually, I take that back. This is also tensor is a superclass, but in this case, we are just saying print A and print B and execute it if it's a tensor and execute this if it is of type int. Let's see what happens when we supply these two functions. These two cells are essentially just setting up the function. And now, in this case, we're not passing it a tuple, we're just passing it an int3. And as I explained, int is a subclass of this abstract base class numbers.integral. Therefore, it executes, because numbers.integral is the closest type match to the type that we are passing in, it will execute B. So here it executes that.
Sorry, I have like a pretty stupid joke. What if the initial encodes was of type int, not numbers.integral, and then like the one that had the tensor was
Here?
of type just int? Yeah, just int.
I think it will probably, my guess is it'll
Yeah.
execute that and not this.
Yeah. Oh, okay. Because it's further down the hierarchy.
Yeah, well, actually, yes, that's correct. Because it's further down the hierarchy and it's a better match. But the other interesting question, which I didn't thought of, and again, you can play with these things. I just didn't want to do it because it'll screw up my rest of the notebook. But another interesting question that occurred to me is what happens if you supply a tuple, and the first is of tensor image, and the second is an int. My guess is it will probably still execute on the first because while it's not an exact type match, it still matches because you have supplied tensor here. If you go up the class hierarchy, you still get tensor. So my guess is it will still execute that. But I would like to play with it to see whether it only executes if the subtype matches and not the supertype. But already I think I get the answer because this is numbers.integral, and when I supply an int, it still executes. So that means if I supply a tuple of value mti and an int, and this is still a tensor, I still expect the function to execute on both pieces of the code. But you can play with it and see what you get.
All right, cool. Thanks.
So those are kind of things that you can do to really, kind of gain a better understanding of how things work under the hood, so to speak. Now, let's see what he does here is he defines the transform tensor in, here is a question, answer to your question too.
Yeah.
Right, so he defines int, and now you'll see that it will execute C. Do that. You see that?
Yeah.
Execute C. So it skipped that, did that. Right. So that's interesting. Okay. Again, we've been playing with the same function. Let's return it to its basic, except now we introduce the decodes part of the function. So what we do here is define the same norm transform, except it encodes and then decodes as well. And the decodes is just the opposite of encode. So x times self.s and then add the self.m back. That's the decodes. So return to basics with a decode. Remember, both of them are defined on only my tensor image. So it ignores the label, only executes on the first part of the tuple you supply to it, if you supply a tuple. So now so this subsequent thing is kind of going in the opposite direction. So you go do the same definition, define MTI to be my tensor image, and norm it. So you see that when you just supply the single value, it norms it. And when you do now, here's another detail. We covered it before, but just to highlight it. When you're actually calling the transform, you don't need to say f.encode. You just call it, because what happens behind the scenes is a dunder call is passed on to the encodes. And we'll see that when you get into the definitional code of transform. So when you're calling the transform, you don't say f.encodes or encode. You just say f of MTI, or basically you're just saying norm of MTI. But when you want to decode, then you need to say f.decode and then pass in the value, because .decode is what calls decodes of the transform. So when you're calling, it means encode. When you want to call decodes, you say the transform.decode. So that's a slight difference in encode and decode. And setup is f.setup as well. So you decode. So remember what has happened here is the transform has run on the tensor image and it has normed it, subtracted the mean and divided by the standard deviation. We want to get back the original image. You do f.decode of the normed image and you get back the original image. So this is the reason, or f.decode, and you want to store. So when you say f.decode, and you pass in the normed image, not the original image, because obviously you want to pass it the normed image so that it can decode it back to the original image. And Sorry, the
Weird
question?
behavior. Yeah, like I just saw a weird behavior I haven't picked up before. Like if you should index into a subtype, like sorry, a subclass. In our case, this my tensor image. When you index into it, it doesn't retain the type. It makes it into a tensor. Like if you can scroll up a bit, can you like scroll to the previous cell? Like when we got the norm image and we indexed into it 12 to 15, it became a tensor, it became a type tensor. No longer my no longer image what was it called? My image tensor or something like that. Do you follow?
No, I didn't get. Are you saying is the type of an image the my image? Is that your question?
Yeah, the initial type of an image is supposed to be a my tensor image. Yeah.
Correct. No, actually, the initial type is tensor. We convert it to my tensor image.
Yeah, yeah. Okay. But when you index into it, it changes the type to a tensor from what is shown in the results. I don't clear. Because if you look at the decodes is only running like in the decodes in the when you define the function. When you define
Oh
the
no,
class.
that because I didn't show you. You know, I have to. Okay, no, that because I'm subsetting or indexing in here, and I
Yes,
can do the
yes,
same
yeah.
thing here as well. But I'll need to put f dot decode into some value and then index into it.
Yeah. So I'm just saying that when you index into it, it like the type changes back to the initial type, that is tensor type.
Yeah, there are rules. You're saying here it is a tensor, whereas here it's a my
Yeah,
tensor
yeah,
image, right?
yeah, yeah,
That is something that is the result of the type dispatch that it does when it takes it into, and we'll get into that detail. Yeah, that's a good observation. That bottom line, what you're saying is f of MTI, and it results in a tensor, but when you decode back, it puts back the my tensor image on it. Yeah.
Yeah.
So the key here is to say if my tensor image and I supply a my int to it, and then let's say f tuple is f of image tuple here, then the transform works on both portions of MTI and MI. And obviously, let's see what we have defined in the transform is only if it is my tensor image. So we should expect that this particular transform that I just executed, sorry, I'm in the wrong place. I need to get, yeah. So when I execute the f of image tuple, then what I should get is the f tuple. And because it's only f is only defined, both the encodes and the decodes are only defined on my tensor image, you should expect that the label part, which is the MI part, should not be changed. So let's see whether that's the case or not. Yeah, we still have a 1. So it hasn't done anything to this 1 because we only define encodes for my tensor image. Now, if we apply f dot decode to f tuple, then you see that you get back to original image. And you kind of can go back and forth. That is to say, again, remember that the encodes and the decodes are only defined on my tensor image. So if I were to put this result of f dot decode in something else and I were to view it, I'll only see that the image portion of it is changed and the integer value of it is not changed. In fact, it shows it right here. So one of the things that we would like to ideally do is not just run one transform such as norm, but we'd like to run a set of transforms. That's essentially what we do when we do the data pipeline, right? Not just a single transform, but a sequence of transforms, if you will. So let's say we want to flip the image. So we are flipping, let's say, the my tensor image of, or defining a function. Again, saying execute it if it's of type my tensor image, and we are just saying flip it if my random number that I choose happens to be greater than 0.5, otherwise leave it as X. So this is something that you may be doing in a augmentation transform, flip it with certain probability, for example. So after you create my image, you want to kind of flip it with some probability. And you define that function. Now, I think in this case, because I've run the notebook and it kind of previously and it might end up working, although if you try it with a fresh notebook, it actually does give an error. If you try running the f of image tuple and then run flip image on a tuple, and maybe I can just, if I remove this my tensor image and make it just flip image X, maybe it doesn't work. But in this case, I've seen sometimes it works, sometimes it doesn't. Technically, it shouldn't, but in this case, it does. I think it is because I've defined this way, but it's not
I
super
remember this
critical to
happening.
why he's just trying to explain that a sequence of transforms should be is typically a composition, and you can make a composition using a pipeline. Sorry, somebody was going to say something.
Sorry, Srinivas. I was just saying that I remember this happening too. And then it suddenly started working for him. And I purely think it's because of the rand there. The
This
first
thing
time
here.
it didn't go through the rand and the second time it did. So that's why it broke and didn't break.
Okay. Yeah.
So that was the reason. And I think the issue was, I don't think with respect to the my tensor image that you're passing in, I think torch.flip kind of changed and you had to just pass in the right values. I think what you've done now is the updated one where you pass in.
Yeah, I had to pass in a tuple.
Exactly.
Here. Yeah.
And I think that was the only change and it worked.
Okay. Yeah, it did work. No, what I meant was here it's working when I don't want it to work. By that, what I mean is, see, ideally, or not ideally, in what he's trying to illustrate in the walkthrough, if you see, is flip image is not defined on a tuple, and so it should give the same error as what you saw on the original function because it's not defined to work on a tuple. This is just a function. That function shouldn't work on a tuple in a traditional Python stuff.
So I guess it didn't flip it. So that's what it didn't go through the random. It actually gave you back else X.
Okay. Yeah.
Maybe that's what is happening. But yeah,
yeah.
What you're saying, that's what should be happening.
That's what I meant by.
Okay. Right. Okay.
In this case, it should have given me an error, but like you say,
right.
It may be the fact that it didn't even execute the function. So it just said, oops, I just, so why would I give you an error if I'm not even running anything on it?
Right. Mm-hmm.
So that depends on the error operations of Python. So anyway, to make a long story short, the point is that if you defined the flip image as a transform by decorating it with an add transform, then it should work on a tuple. It already worked, but as you said, it may be because of this random value that it worked on that instant may not work in other instances when you try. But this decoration by transform should definitely work. So if you do the definition, then define an image tuple and look at what you're doing. You're actually executing F, which is you're encoding the image tuple first, and then flipping it and putting it in ttup, which is the transform tuple. Then it works and shouldn't complain. It's actually applied the flipping of the image with a probability of 0.5. It may or may not have flipped it. And then ttup kind of gives you the execution of that transform. Now, the important thing here that we are kind of focused on is to say, we'd like to do the sequence of transform. Now, I illustrated it with 2 transforms, one after the other, and use that to illustrate what we eventually want to do, which is build a pipeline. So a pipeline is nothing but a composition of functions. So a compose is a basic Python capability as well. It just puts together sequence of functions, and the output of each function is passed into the input of the other, and then the functions execute one after the other. So you can define a pipe compose, pass it in F, pass it in flip image. Now, notice the order. You pass in the first one you want to execute first, and the second one, that is the outside one, so to speak, as the second. And you define that composition, and then you do a pipe of image tuple, and that should work as well. So if I printed out ttup right now, it will give me the same example as this. The problem, though, of just using a composition versus a pipeline is the fact that a compose doesn't have a decode. So you can't, after composing this, you can't say, oh, give me back the decoded image, because there is no decodes to the compose. Right? So even though you defined it, I mean, you point it as a pipe, but there is no compose.decode. So if you do a pipe.decode, obviously you'll get an error because there's no decode to pipe, which means there's no decode to compose. So in order to do that, what you will need to do is to say, because both flip image and F are transforms, and remember what I told you about decode and encode. If they are not defined for a transform, they are no ops. That is, they just return the input as the output. So flip image doesn't have a decode. So when you do a flip image dot decode, remember that a dot decode always exists in a transform. It may not do anything if it's not defined. So basically a flip image dot decode, and when you pass in a ttup, which is what was the output of the transformation previously, then you just get back what you sent in. And then F, remember F had a decode, so it will decode the output of this first internal function, that one. It will decode that and will return the tensor image. But this is a fairly obtuse way. So you have to remember the sequence of transforms that you applied and then call the decode in sequence and pass it in. This will work, but it's a fairly involved way of invoking that. So what he does is comes up with the definition of a pipeline, and you supply a sequence of transformation by putting the transforms into a list, and you apply the pipeline code to it. That is the pipeline, make it into a pipeline class. And again, we'll go in 2 or 3 lectures into the details of pipeline code. But here we just pass in the 2 transforms that we want applied, or that we want to supply as input to the pipeline class, and create a pipe. And this pipe, because it's a pipeline, will have a decode. So now when we go forward, that is to say pipe of image tuple is ttuple. That means it executes. Now remember, I told you that when you call a transform, you just call its encode. So similarly, when you call a pipe, it executes these in, and we've seen this before, it executes it. If all of their order values are the same, it executes in the sequence it's applied. If the order value is specified, then it executes in the order sequence that you have specified within the transforms, and it executes them in that order. So either way, it executes the encode function of each of these transforms in the order in which you've specified. And if you do the decode, it goes backwards. So here, instead of having to call the complex, where was that? Flip image dot decode, pass it ttuple, and then call f dot decode on that, we can just create the pipeline. While going forward, just call the pipeline on the image tuple, you get the transform value. On going backward, you just do pipe dot decode on the ttuple, which is the transform tuple, and you get back the original image. So by creating the pipeline class, he has made the sequencing of transforms and applying encodes and decodes on them very simple. Okay. Again, here The point he's trying to illustrate here is sometimes what you can do is just supply a function instead of even a transform to a pipeline. And once you supply something to a pipeline, supply a function to a pipeline, it knows, the pipeline class knows that it needs to convert a function into a transform and run it. So anything supplied to any function supplied to a pipeline gets converted to a transform within the pipeline class. So we execute that and we pass it in, and again create the pipeline, the flip image. Remember, you see that I've removed the transform decorator from it. So the flip image is just a function now. But I do an image tuple and I run it on the T tuple and I do the pipe.decode and it still all works. And the point being that a flip image, even though it's just a function, by the time you pass it into a pipeline as just a function, the pipeline class converts it to a transform and runs its encode when we call it here. Any questions? Okay, now just a little bit more that what he tries to point out is the fact that early on we created is, I forget, somebody highlighted and pointed out that, hey, we create a my tensor image class, which is what the MTI was, but FastAI already, besides having the tensor base, it already has a tensor image class, which is equivalent to kind of my tensor image. So you don't need to create your own my tensor image class. You can just use the tensor image class, which in turn inherits from the tensor image base class. So you can see tensor image is nothing but just the, it's essentially there is no code in there. And the tensor image class is just pass stuff. And then, so you can see that, definition of tensor image in FastAI is equivalent to my tensor image, and it inherits from tensor image base, which probably inherits from tensor base. But bottom line is you can define MTI to be just a tensor image. The tmate.clone just makes a copy of the tensor image values. And by the way, this int or class with a capital I is an interesting thing. You can kind of go look at it yourself and play with it. But bottom line, what it does is, again, has nothing, no definition in it, but you see that there is a show print defined. So the capital int class in FastAI, and we'll see that we'll see the code or the utilization of it subsequently. But the interesting application of it is its ability to show itself. So it's an int class which can show itself. So when you run a decode on it or something, it can print itself on the screen. A normal int class doesn't have that capability. So it just adds a show int capability to the int class and puts it into a capital int. By the way, there is a capital float equivalent to this as well. So let's just define mi to be the capital int class, so it can show itself if we need to, and then go through the same sequence of steps just to illustrate that nothing has changed, and we can execute the same sequence of pipe. And obviously the one important thing is, instead of being my tensor image, you will see up here that it's of type tensor image, because that's what we have defined MTI to be. So we don't need to define our own class. We can just, a subclass of the tensor base class is already being defined for us. And that's the subclass that we can use. And when we use transforms and we want to differentiate an image from something else, we can just use the tensor image, which is a FastAI image tensor capability. And again, keep in mind, why do we care about it being a tensor image? Let's say we are decoding multiple values or encoding multiple values in our data tuple, and there is an image and there is a text. By the time we get deep down, both of them could eventually become tensors. But we want to differentiate between the two and do different things when we encode or decode them. The way we can do different things is by specifying different types to them. So in one case, we'll give the type tensor image, and in another case, it could be, tensor text, or, category tensor or something else. So then we can say when we encode, apply it only to this type and not to the other type. So that's the reason for the subclasses of these various types. And then the last piece of the puzzle is not only can you do all of the transform and make the transform from the pipeline when you're doing the flipping of the image or the norming of the image, you can do that and create a transform of the loading part as well. And see, what you do is you define the function to create a tensor. But in this case, we tell the function through a transform to return a tensor of type tensor image. So way up in the code, if you look in the notebook, we would, interest of time, I'm not scrolling up again, but if you see, we would have done tensor array load image and then subclassed it. Here we are doing that and saying, return me a tensor, but make the tensor that is returned of type tensor image. And you can do that by typing the return value and making the create image transform, create image tensor transform. So that's what that is. And actually the cell below that just illustrates that you need not have a transform decorator. You can even just do a pipeline. And as I said before, as long as you specify a function in a pipeline, it automatically converts it to a transform. So you create a tensor image, and you can see the type is of tensor image by executing that function. And so you check the type, it's a FastAI2 torch core tensor image. You go through the same sequence and you define an MTI to be of type tensor image. And the second part of the tuple, same as in, do the same definition of flip image. So I call it MTIs, the norm, image tuple, execute the pipeline, going forward, do the decode, coming backward, and it's one. Now, just a few comments before we close. In the walkthrough, he talks about as item as being an important variable that is supplied. It turns out that as he moved forward in the code, he completely got rid of that concept. All transforms treat inputs as tuples. And if you give it a list, then its behavior is different. And so transform treats passed in values as tuples, and the behavior is for the function to act on each item of the tuple, of course, conditioned on types, as we saw in this whole walkthrough. There's no, there is a different type of transform we inherited from transform. That transform is a default definition of transform, as we'll see in the code. I think in the next class or the one after that. There's also a subclass of transform or a different type of class of transform called item transform. And in that case, what happens is it treats the thing that's applied to the transform as an item, as a single thing, rather than as containing various elements within it. And in some cases, you want that ability to do that. Eventually, you still want to process every item in it. But the bottom line is there are times when you want the transform to tackle the thing that's passed into it as a tuple and therefore act on every element of the tuple. In other instances, you want it to act on the single item that you pass to it. And depending on where you are in the pipeline or what you're doing, for example, when you're building a data set, you want to give, for example, in the pets, and that's what I talk about in this paragraph, you are applying one pipeline to build X and another pipeline to build Y. In that instance, for example, you want each of the pipelines to act on items. However, once you have built the X and the Y, you want to combine the X and Y as tuple. And from that point on, you want it to act as a tuple, or you want the transform to act on its input as if the inputs are tuples. So depending on where you are on the overall data processing pipeline, you may want a different behavior from transform. And you can get that by either using the default transform, which treats its input as tuples and acts on every element of a tuple, or you can go define a transform and inherit from item transform, in which case the transform treats what you give it as a single item. And you can play with it to figure out when and where it is useful. But that's a change from what he talks about in the walkthrough. He has simplified the code to where the default behavior is that of handling the input as tuples. And so you only need the exception, and you specify the exception by inheriting from an item transform. Okay, so that's the end of that notebook. And I kind of posted this notebook last week itself. So if there are any questions, we can go through it now.
So Srinivas, could you scroll up to the place where you use the decorator twice in a row? On it's way earlier in your notes.
Oh yeah, you mean where where there were multiple encodes specified?
Yes, yes, exactly. Yes,
Okay,
exactly.
yeah, sure, got it. Yeah.
Transform.
Let's say another way, so that's what I'm looking for, because it's one way, and then I say there's a different way of doing it.
Another way.
Yeah, I think that's it. You just passed. You just passed.
Yeah.
Oh,
you
did
just
I just pass it?
Yeah.
Another example.
No, this is another example.
Yeah.
About
I think it'll
before
say,
that, yeah.
I think it's about that.
Yeah.
Here.
Yeah. So this behavior is called function overloading, and this shows an example of it, right? I mean, you're actually building into this function two kinds of behavior, but by these two consecutive decorator statements. But you could build in many more types of behavior by just using more and more decorator statements, right? It's making the encodes function behave differently according to what its input is.
That's correct. Yes, but actually it's not just one. It's a, the thing is, it's defining a variety of methods, and that doesn't typically work with native Python, because you can't define the same method to work differently. Only one of them will apply in native Python. Here, he builds in the capability in the infrastructure to support multiple encodes depending on the type. That will not work in native Python. If you try the decorator with the same method within the class and you supplied it, either it will complain or it will just use the last one.
I tested it and uses the last one.
Yeah.
Yeah, so it's just that this is kind of interesting to me, because you always read about overloaded functions and so on, and this is actually how to create that kind of behavior for yourself.
Right. It's actually overloaded. You can say overloaded methods. Right. But the other key point I wanted to highlight is that it's not. It is overloading in that sense, but yeah, you're right. It's overloaded methods.
Yes.
And overloaded methods aren't supported in native Python because it will just use the last definition.
Mm-hmm. Mm-hmm.
And how he builds in the support for this is something we'll look at in the lecture after next, of when we dive into the code for, actually even there he uses actual examples of transforms. And then in lecture 5 is fairly long and detailed, and 5, 6, 7 are the most complex because he dives into the Python details. But we start off easy, and we'll dive into the transform and pipeline code, which in turn leads to the changes in Python that support this overloaded methods, as you're calling it.
Yeah, so this is great, and thank you so much for all the work you did to present this material. It's really helpful for, I think, all of us to see it clarified in the way that you've done.
Thanks.
Yeah,
And I'll also just, sorry, but one more thing. I'll post some slides about lecture 5, which is at least the beginning of it. It goes through the data block API in various forms. And if time permits, thankfully this lecture ended in one lecture. So because I think lecture 5 will take us 3 or 4 lectures to get through, because there's a lot of material to get through, and also inherent base like meta type and meta classes and preparation of classes and other things that, even a intermediate Python programmer may not have always encountered. At least I never, I used it in passing, but never to the detail that Demi gets into. So I'll post the slides of, it's an easy start, and it's just a data block API, some slides to go through, but we'll start with that and then dive into the notebooks as we get into lecture 5 next week.